Hi everyone. Today let's talk about session 6.3, volume by slicing. Big idea. The integral can be used to compute other geometric quantities besides the area under a curve. It can be used whenever you can break up a problem into some of an infinite number of infinitesimally small pieces. So when the solids can be divided into thin slices along the x-axis, then, well, we're gonna have the washer method or this method, okay? And if it's solids of evolution about the x-axis with no cavity, and so we get disk. And if they have contains cavities, we can have washer. So today we're gonna talk about this method and washer method, okay? Big skills. You should be able to calculate the volume of any solid by breaking it up into thin slices and integrating the volume of each thin slice. So definition. Let S be a solid that lies between x equals A and x equals B. If the cross-section area of S is in the plane px through x and perpendicular to the x-axis is a of x. So this is a picture. Okay, we have S is the solids. And then at the x-axis, let's say we have the point x. And let's say we have a plane that goes through x and perpendicular to the x-axis. So this is a plane. Okay, and we use this plane cut this solids into, and the cross we get the cross sections area. Let's say this cross section area is a of x. Okay, so how do we integrate? How do we find the volume of this solid? Well, we can think about, okay, we have this guy and we cut it into the slices, and what is each slice looks like. So each slice looks like this. You have this is like a cylinder, right? You have this is the height, and the area of base is the cross section area. So do you remember cylinder? The volume of cylinder is area of base times height. So if we have a circular cylinder, then area base is pi r squared. But in general, any cylinder, the volume is going to be area base times height. So that's why here, that's why here we have the volume of each slice is the area base, which is A times X. This is the cross-section area times change of X. Change of X is the height. So far, so good, everybody? And then the area of solids is just we add those up. So that's why you have here the limits, so let's change of xi goes to 0, and then we have those a of x. So this is, let's say xi bar is any point, is a point over there, over that interval. Okay, xi minus 1 to xi. So this is like a Riemann sum. So, but anyway, you can use this simple version to get the idea. This is the integral. This is the sum of the volume of each slice. And for each slice, we have the area base is the cross-section area times the height is change of x. So that's why we get this integral from a to b, a of x times dx. Okay. So keep this in mind. Let's solve our example. So example 1. A solid has a base that is bounded by the curve y equals x squared and y equals 2 minus x squared in the xy plane. Cross-section through the solids perpendicular to the x-axis are semicircular disk. Find the volume of the solid. Okay, so first of all, let's look at the 2D picture. So let's look at the base. What's the base? So let's draw the base. So we have, okay, let me make it more. Okay, so we have the the curve y equals x squared, well, y equals x squared looks like this, right? This is y equals x squared. How about 2 minus x squared? Well, 2 minus x squared also pass through minus 1, 1, and minus 1, 1, and this 0, 2. So, oops. Okay. So it looks like it's a parabola, but open down, right? And we want to, so the base is bounded by those two curves. So this guy is our base. And we want to construct a solid on top of it. Okay, the cross section through the solids perpendicular to the x-axis. So this is the x-axis. And then it talk about the cross section perpendicular. So this is the cross section perpendicular to the x-axis, semicircular disc. So on top of this green segment, you're gonna build a semicircular disc on top of it. So let's draw a 3D picture, and I can show you what it looks like. So 3D picture, let's say we have, this is x-axis and this is the y-axis. So it's like we have an xy plane laid down. And then, oops. Okay. So this is the z-axis. So far so good, everybody. And let me use the purple color to indicate the base. So the base passed through the points 0, 0, 1, 1. And minus 1, minus 1. So this is the first. Okay, so this is y equals x squared. And on the other one, I pass through 0, 2 and connect these two together. So this guy is y equals 2 minus x squared. So this guy is our base. And then to construct the solids, okay, so the cross section for the solid is perpendicular to the x-axis. So perpendicular to the x-axis, so this guy, we're gonna construct a semicircular disc on top of it. So let's say if right here, semicircular disc on top of it. Okay, so that's why we can get a solid. Can you imagine a solid on top of this region? Yes? Okay, so now how do we compute the volume? Okay, so the volume is, let's look at our x. Our x goes from minus 1 to 1, right? And we want to use the A of x is the area of the cross sections, and then dx, right? What is the area of the cross section? Well, this is the area of the cross section, right? But it's a semicircular disc, right? So it's a semicircle. So semicircle is what? Semicircle is, you know a circle is pi r squared. So semicircle is 1/2 pi r squared. But what is r? Well, r is half of this green segment, right? Because this green segment is like the diameter of my circle. So r is half of that. So that's why r is half of, but what is this green segment? We use the upper curve. What is the upper curve? X squared minus the lower, upper curve is actually 2 minus x squared. Minus the lower curve is x squared. Oh, so we have, this is 1/2 times 2 minus 2x squared. So when we distribute the 1/2, we get 1 minus x squared. So this is the r. Okay, then what is a of x now? Is 1/2 pi r. R is 1 minus x squared. Okay, so this is a of x. Finally, so my v is integral from -1 to 1, 1/2 pi, 1 minus x squared x to the square. So this is our integral. So far, so good, everybody. And can you see the left side and the right side, they are symmetric? Okay, that's why instead of calculating for x from -1 to 1, we can calculate from 0 to 1, and then we have 2 copy of that. So I love the 0. Do you? So sometimes the 0, when we plug in polynomials, a lot of terms just get 0. So that's why I want to work with the 0. Okay, so if you see the solid is symmetric about the y-axis, it's enough to calculate half of them and then multiply by 2. And furthermore, you see this 2 and this 2 cancel. So we get pi integral from 0 to 1 of this guy. Well, this guy, you can see if you try to use substitution, it won't work, because if you try to let u be the inner function, your du, you want to see the x multiplied to it. That will contribute to your du, but you don't see any x there. So the only way to solve this integral is to multiply out and then use power rule. So let's multiply out. Remember a plus b squared is a squared plus 2ab plus b squared. A minus b squared is a squared minus 2ab plus b squared. So this guy is 1 minus 2x squared plus x to the 4th dx. Okay, let's integrate. So integral of 1 is x. And then we have x cubed over 3, x fifth over 5. Evaluate from 0 to 1. Okay, that means we plug in 1. Subtract, we plug in 0. Ooh, it's all 0. Isn't it nice? And then 1 minus 2/3 is 1/3. So 1/3 plus 1/5. The common denominator is 15. That's 5 plus 3, which is 8. So our answer is 8 pi over 15. So far, so good, everybody? So in this example, we first draw the 2D picture for the base, and then we draw the 3D picture to figure out what is the cross section look like. We know the cross section is a semicircle, so the area is 1/2 pi r squared. But what is r? Well, r is half of the difference between the two curves, right? So that's why we compute the r, and then we can plug in our formula, and we realize, okay, we're not able to use u substitution, because if you let this be u, your du is negative 2x dx. So you need the x right there, but there's no x right there, so we cannot use u substitution. And then it's okay, we can multiply it out and just use the power rule, and then we can plug in the numbers and evaluate the integral. So far, so good, everybody? Okay, time for the disc method and washer method. Okay, so suppose you have a cucumber, right? Have you ever cut a cucumber? Okay, have you ever cut a cucumber or potato? Then what do you get after you get a slice? Well, the slice, it actually give you a circle, roughly speaking, a circle, right? So let f be continuous with f greater equals 0 on the interval a to b if the region R bounded by the graph of f, the x-axis, and the line between a to b is revolved about the x-axis. So this is the function f, and we revolved about the x-axis, then we generate a solid. Okay, and then the volume of the resulting solids of evolution is pi f squared. Why is that? Oh, see, we cut it this way. This is my rectangle, right? And then the width is dx. Okay, so what is this guy? Well, this is the sum of, well, this is a circular cylinder, right? So that's why area base is pi r squared and height is dx. But my r in this case is actually my f of x. That's why you get this, remember, sum becomes the integral, the Riemann sum. When the number of the slices goes to infinity, we get the definite integral. And then r in this case is just f of x. Okay, so that's why we get this formula. And by the way, we do not provide formula sheets in the exam. So for all of these formulas, please understand them. So actually when you draw the picture, you realize, oh, it's the sum of the volume of each slice. But each slice is like a cylinder. That's area base times height. So you understand the picture and then you can write down the formula automatically. Okay? So understand the formula, not just memorize them. Okay? Next, Washer method. Let f and g be continuous function with f is bigger than g of x on the interval from a to b. Let r be the region bounded by them. So this is r is the region bounded by them. And if we rotate about the x-axis, okay, see what happened? We will get this solid. Now, we also can cut it into slices. But when we cut it into slices, well, each slice is not a circle, it's actually an annulus, right? So because it's still so it's like with the cavity, right? So annulus, what is the volume of this cylinder? Okay, it's still area base times height, but area base, the base is pi big R squared minus small r squared, right? That's why here with sum pi area base big R squared minus small r squared and height is still dx. So that's why the big R is is f, the small r is g. So that's why you get this formula. So far, so good? Okay, we mark. If the region is revolved about the y-axis, we get integral with respect to y. So here in this case, you see we have big R and small r, and they are vertical distance. So given any functions, we know the vertical distance is the y, and then the horizontal distance is the x. So that's why if you rotate about the y-axis instead of the x-axis, well, your formula is gonna change. Okay, you replace the x in by y. So today we will do tons of examples, and I will teach you how to think, okay, and how to decide which method to use and how to whether we want to have an integral about x or integral about y. So are you ready? Okay, let's start. Example 2. Find the volume of the solid obtaining by rotating about the x-axis the region under the curve y equals e to the x from 0 to 1. Okay, so let's draw the picture. E to the x. Remember, I asked you to memorize all the common graphs. So e to the x looks like this, right? And this is the point 0, 1. Okay, so this is e to the x, and we're looking for from x from 0 to 1. So at 1 is e, okay? And we want to find this area, right? So not this area. Oops. We want to use this region to rotate. Oops, sorry. Let's see. Okay. All right. Okay. So we want to use this region, and we want to rotate about the x-axis. So this is the x-axis. What happens if we want to rotate about x-axis? Well, you're gonna get a solid, right? Okay. So here are the steps how to solve this kind of problems. Okay, so every time when we see a new problem, I want to summarize the steps with you. Okay, and when you do another problem, well, you just follow the same steps. Okay, so here are the steps. First, we're gonna draw the graph. Okay, and we also want to know which axis we want to rotate. Okay, what is the rotation axis? So here we draw the graph, and we know we're gonna rotate about the x-axis. Okay, this is the first step. Second steps, you want to find the region you want to rotate. So in this case, this is the region we want to rotate, right? And next, you want to draw rectangle. Do you want to cut it vertically? If you do, the width is dx. Do you want to cut it horizontally? If you do, this is the width is dy. So it really depends on whether how you want to cut it vertically. Okay, so in our picture, so we know our solid looks like this, right? So it looks like the cucumber is laying this way. And how do you cut it into slice? You don't cut it like this, right? The cucumber looks like this way, you cut it like this. So that's why we know we're gonna cut it vertically. Then this is dx. Is that okay, everybody? So, and you can imagine usually the rotation axis is like your cucumber look, gonna lay it in that direction. So here you rotate about the x-axis, so your cucumber is laying on the x-axis, this direction. And when you cut it into slice, you cut it vertically. Okay, so I don't want to occupy so many space, so let me just draw a small cucumber here, and then we know we're gonna cut it this to form a slice. Okay, so this is the second step. The third step, okay, we're gonna draw what happened to the end point of the rectangle when we rotate the rectangle about the rotation axis. So far, so good, everybody? Okay. Let me see. Oops. Okay, do I press something? Okay. So, in our case, wow, you see, this is a very thin rectangle. So just imagine there are only two endpoints. Okay, this is, imagine it's so thin, it's like a line segment, so it only have two endpoints. So we want to draw what happened to the endpoints when we rotate about the x-axis. So what happened to this point? Well, when you rotate about the x-axis, it just stay there, right? This endpoint, it just stay here. And what happened to this endpoint when you rotate about the x-axis? We get a circle, right? So if you see a circle, then it's gonna be disc method. Then we know the area of circle is pi r squared. So in this case, what is r? Well, r is from the point on the circle to the center, right? And remember, if you have any function, vertical distance is y, horizontal distance is x. So in this case, we're talking about vertical distance. So r equals y. But because it's dx means our integral is in terms of x. So if you have dx, you're gonna have, this is gonna be, we get integral of x. If you see dy, we're gonna have an integral of y, respect to y. Okay, so that's why if you have y, express your y in terms of x. So y equals e to the x. And then we're ready, right? So this method, when you see a circle, you have this method. If you see an annulus, then that is washer method. And then the area of annulus, pi big R squared minus small r squared. Okay, so these are the steps. So let me change back to my green color for this problem. So my volume is the integral, okay, my x, remember this is dx. So my x goes from 0 to 1, and then pi r squared. Well, r is e to the x. This guy squared. This is my integral. So far, so good, everybody? Okay. And you can see pi is a constant multiple. We can pull it out. And e to the x squared, this is the same as e to the 2x. How do you integrate e to the 2x? Well, it's e to the 2x, but you divide it by 2, right? Evaluate from 0 to 1. We plug in 1 first, so e to the 2 over 2. Minus, we plug in 0. Be careful, it's not 0. E to the 0 is 1, so this is 1/2. So, this is our answer. So far, so good, everybody? Okay, so from the remaining examples of this sessions, we're gonna follow these 3 steps. Okay? So, I'm so worried about some students. They draw a lot of things on this graph and make it so complicated and so mess. So I hope you only draw after you draw the graph, only draw the little rectangle and only draw what happened to the end point to the rectangle. Okay, when you rotate about the rotation axis. Okay, so don't draw a lot to make a mess. Okay, draw very clean. Then you can see, okay, we have circle. 1 circle give us this method. 2 circle give us washer method. Yes. So, I don't know, do you like drawing? So, in this chapter, you're gonna draw a lot. Okay. So, example 3, find the volume of the solids obtaining by rotating about the x-axis, the region under the curve y equals x squared minus 4x plus 5 from 1 to 4. Just set up the integral. Do not evaluate. Okay, so let's draw the picture. So this is the x-axis. This is the y-axis. Okay, so we know this is a parabola and it's opening up because the leading coefficient is positive. And we want to draw it from 1 to 4. Okay, first 4. Let's plot some points. When x is 0, you get 5, right? So 0, we get 5. And when we plug in 1, 1 minus 4 plus 5 is what? 2, isn't it? So at 1, we get 2. Okay, so let's... And when 4, let's plug in 4. 4 squared is 60 minus 4 times 4, 16 plus 5. Ooh! At 4, we also get 5. Okay, but so I would say, because it's a parabola, I would say this is the same point. Okay, let's try to plug in 2 as well. 2 squared, 4, 4 minus 4 times 2, 8 plus 5. So it's 1, right? Okay, so it's 1 here. So we connect them smoothly. Okay, so this is the parabola, and we are looking at the region under the parabola from 1 to 4. So this is the region, okay? So this is the region we want to rotate, and we want to rotate about the x-axis. So far, so good. So this is the first step. we sketch the graph, and then we figure out the region, and we write down the rotation axis. Second, we're gonna draw the rectangle. So let me use a different color so you can see. Okay, so I want to draw the rectangle. So because my cucumber look like this, right? So I want to color it vertically. So that's why my rectangle laid vertically. So this is gonna be dx, right? And what happened to the endpoint to the rectangle when we rotate about the x-axis? Well, this point stay there, right? And this point, well, we rotate and then we get a circle because we only have one circle. So the distance from the point on the circle to the center is the radius. So the radius in this case is the, remember, a graph, and this is the vertical distance is y, horizontal distance is x. So r in this case is y, and y is x squared minus 4x plus 5. That's why volume is integral, my x goes from 1 to 4, pi r squared. Well, r squared, r is x squared minus 4x plus 5 squared dx. And in this problem, we just need to set up the integral. We don't need to evaluate. And that's it for this problem. So far, so good, everybody. See, we follow the same steps. Sketch the graph, and then write down the rotation axis, and then decide whether you want to cut it vertically or horizontally, and then draw what happened to the endpoint to the rectangle when you rotate about. If you get a circle, that is this method. If you get an annulus, that is washer method. Okay, next. Example 4. Show that the volume of a cone of height h and radius r is 1/3 pi r squared h. So do you know this? This formula? Okay, we know for a circular cylinder with radius pi and height h, with radius r and height h, the volume is pi r squared h, right? And we know that a cone with radius r and height h, okay, my cone doesn't look pretty. Okay, so this is gonna be 1/3 pi r squared h. But do you know why this is 1/3? Did your teacher prove you why this formula is true? So when I was small, so I learned this formula in my elementary school, right, in geometry class. And then one day my teacher, she bring a glass cylinder, and she also bring a glass cone. And what she do is she fill the sand into the cone and fill it all up, and then pull the sand into this cylinder glass, and then I can see roughly, well, it looks like this guy is 1/3 of the height. Then I know, oh, the formula is 1/3 pi r squared h. So this is how I learned this formula the first time. Okay, my teacher was using the sand to pull over there. Okay, but today we can actually prove it. Okay, so we can actually prove why this formula is exactly 1/3. Because what I know, okay, it looks like 1/3 of the height, but it just looks like. So I trust this formula, but it's not really a proof, okay? A formal proof. So today, after we learn Calculus 3, we actually gonna prove it. We can prove it right now. Okay. So how do we prove it? We want to transform this problem into xy coordinates, okay? So we want to design, so I would say, okay, let's consider the line, okay? And I want to have my So remember, if I rotate, I want to get a cone, right? So this guy, oops, this guy is R, this guy is H. So this point is HR. Okay, so we know a line equation is like mx plus b, but because it passed through the origin, so y equals mx. And how to figure out our m? We can plug in the points hr. So when x is h, my y is r. So my m is r over h. Remember, r and h, they are just constants, okay? They're parameters. So in this case, y equals r over h, x. So this is the line. So far, so good, everybody? Okay, now, what do we do? See, my cucumber look like this, so I cut it this way. So, okay, let me save it first. Kind of slow. Okay, so we want to cut it vertically, then we get the x. So what happened to the endpoints? Well, the bottom endpoint will stay, the top endpoint it generates a circle, right? And the distance from the point on the circle to the center is the radius, but because here we already used this symbol for the parameter, so let me call this guy r, and this r is a function of x. It varies, okay, and in this case it's actually y, so it's r over h x. So volume is integral x goes from 0 to h pi big R squared, which is r over h x squared dx. So far, so good? Okay, and this is, let's see, this is, we can pull out the pi. Oh, furthermore, we can actually, this is r squared, this is h squared, they're all constants. We can put them out. And then we have x squared dx. And when we integrate them, we get pi r squared h squared. This is x cubed over 3, evaluate from 0 to h. We plug in h, so we get pi r squared h squared h cubed over 3. You see, h squared and h cubed, they cancel, only have one h left. Ooh, and when we plug in 0, it's all 0. So then that's why our formula is pi r squared h over 3. So that agree with our formula. So this is the proof. So far, so good, everybody. All right. Okay, I just remember something. So so on our course website, you can see this is our course website. Here you see the GeoGebra projects. So actually, the first GeoGebra project is teach us how to use GeoGebra to visualize solids of rotation. And sorry, this is okay, I'm taking the videos in the summer. I'm recording this video in the summer. So this is my spring 2020 class. So the due dates for your semester might be different. Okay, so the PDF instructions here. Please go to this website and download GeoGebra Classes 6. Don't use the online graphing calculator because I have some students tell me that the bottom there are different than the ones I show in my picture. So please download the GeoGebra Classes 6. It's free software. Okay? And then watch this YouTube video to learn how to use GeoGebra to graph 3D solids. So this is my YouTube video. Okay, so you can follow my videos step by step, and I also provide you step-by-step screenshots in my PDF instruction.
Hi everyone.
in this video. Okay, so you can see I show you how to build up the so the volume of those two solids. Okay, so see, and here I also give you a step-by-step screenshot. Yeah, this project is a little bit longer, but after you finish, you actually can get very beautiful formula. I hope this can deepen your understanding about this concept. I also have some examples here. So here we are in 6.3, right? So for all the examples where I'm able to draw, then I provide the picture for it. So let's see. Example 2, do you remember we have e to the x? So e to the x when my line segments, so this line segments represents our small rectangle. So when my small rectangle goes, do you see this solid it generates? So you can move around. This is the solid it generates. Okay, so that's why the line segment is like our small rectangle, and the radius is actually a function of x. And when the rectangle travels around, and then we can actually generate the solid. Okay, so you can watch this example on our course website. And example 3, do you remember this parabola? See, the GeoGebra can actually help us to graph the parabola. However, in the exam, you won't be allowed to use graphing calculator. So learning how to graph the function is very important objective of our course. Okay, so you can see when the rectangle travels around, we also get this solid. Okay, so you can move this around and you can look at this solid. I hope all of this visualization can deepen your understanding. Okay, can you see? All right, so let's continue. You can see the fourth example we just solved is just the cone, so I didn't draw it here. But all the rest of the examples, I draw it here. Okay, so let's continue. Example 5. Find the volume of the solid obtaining by rotating about the y-axis. The region bounded by y equals x cubed, y equals 8, and 0. See, be careful now, we're rotating about the y-axis instead of the x-axis. So we're going to be careful with that. Alright, so let's draw the picture. So we have the x-axis and we have the y-axis. Okay, and let me draw the x-axis a little bit more down here. Okay, and then x cubed. We know x cubed pass through 0, 0, 1, 1, and 2, 8. Okay, and we pass them through. It looks like that. Okay, so we're looking for the region bounded by this cubic function, and y equals 8. Y equals 8 is a horizontal line. X equals 0 is actually the y-axis. So this is the region. So far, so good, everybody. And we want to rotate about the y-axis, not the x-axis anymore. So how do we cut it? So how do we cut it? See, our cucumber looks like this. Then how do we cut it? We want to cut it horizontally. So that's why here we have dy. We're going to expect to have an integral about y. Okay, integral with respect to y. Okay, so now next steps. We draw what happened to the endpoints. So this line segment, this thin rectangle has two endpoints. What happened to the endpoint when we rotate about the y-axis? Well, this endpoint just stay there, right? And how about to the next endpoints? We go around, oops. Okay, we go around and we get a circle. So far, so good, everybody. We get a circle. Ooh, then this is a disk method. And remember the distance from the center to the points on the circle is my radius, r. So be careful now, because here, any functions, the vertical distance is y, horizontal distance is x. So this r is actually the horizontal distance. And we know we're gonna have an integral about y. So we want to express the x in terms of y. Okay? So what is the x? Well, x is then cube root of y. So cube root of y. So far, so good, everybody? Alright, let's continue. So my volume is my y goes from 0 to 8. And then we have pi r squared. So r is y to the 1/3 squared dy. So far, so good, everybody? And then next, we're gonna have, so let's see, pi, we can move it out. This is y to the 2/3, right? How do we integrate it? Well, that is y to the, add 1 to it. So 5/3 over 5, the third, flip it on top. Evaluate from 0 to 8. We can plug in 8. So 8 cube root of 8, 2 to the 5th, 32, right? When we plug in 0 is 0. Ooh, so 3 times 32, oh, maybe I should put the dots here. Otherwise, it looks like 3.32. 3 times 32 is 96. So my answer is 96 pi over 5. So far, so good, everybody? Alright, so let's come back to our course websites, and you can see example 5. This is the picture. See, we have the cubic function, and when the segment goes around, okay, it's still loading. Give us more time. Okay. So, you see, when the line segment goes around, we actually generate a solid. Okay, so let's go down a little bit. You can see this solid. It generates. So we can move it around and see. Okay, so this is a solid it generates. So far, so good, everybody? Okay, let's continue in our video part B for the remaining problems of this session. Alright, see you in video part B. Bye!